the focus will be more on application part, and of course we'll touch upon most of the theory part as well. So some of the terminology that we'll be starting with. So before we begin with the terminology, so let me first tell you what time series forecasting is all about. Well, you might have already heard about forecasting in other type of econometric models, like regression models and so on, right? There also you do forecasting. Now a question, obvious question that comes to mind, that why another type of forecasting? Why we need to use time series forecasting when we have multivariate forecasting like regression, right? So what happens in regression? You have a y, then you use some sort of x to forecast y, right? That's the multivariate regression. Now in number of cases, your x or the independent variables or the covariates or the factors, whatever you call it, are not available all the time, right? And even if it's available, many times there are restrictions. You cannot use these variables in order to do the forecasting. All right. Many a times you will come up with scenario where you only have the y values, and y values for different time periods, okay, from different time periods, okay, and you do not have any x, or you actually don't know what are the factors or the variables which are related to your y, right? So in such scenario where you only have your single variable or the dependent variable or the variable of interest values are available, you don't have any covariates available, then you go for what is known as the time series forecasting, because you have only one variable in place, right? Time series forecasting. So what you do is that you simply plot the trend of that variable and see what is the pattern in that variable y, right, over time, okay? So over time you simply see the pattern, and based on the pattern, historical pattern, to the future, extrapolate to the future, right? So in normal regression, you used to take the independent variables to do forecasting y, whereas in time series regression, you will use, say, yt equal to yt minus 1 plus some error, okay? Okay, so this will be one simple form of model. Okay, we call this AR model. We'll talk about it later. So here you do not use an independent variable. You or maybe you can say that you are using it, but you don't use a different independent variable. You use independent variable as the I mean the past value of dependent variable as the independent variable. So here is the variable yt, and then we are using yt minus 1. That you are forecasting the value of y from its past values, right? So previous value of y gives the future value of y, right? And of course the error term. So this is one way of doing time series forecasting. So you only have one variable in place. That's why we call it as univariate time series, because we only use one variable, univariate time series. So in this case, we do not have the concept of dependent variable where y is considered as dependent variable, and then there are so many independent variable x1, x2, and so on. So that is used primarily in multivariate analysis like regression, whereas in time series, univariate time series in particular, you only have one variable in place, and that's what you use for forecasting. Well, a time series is a type of series of data or series set of observations on a particular value, okay, and which is taken at different time frame. And one of the best example is stock price, right? Stock price for last 30 days, right? So you have stock price of the same stock for different time periods, right? So that's one example of time series data. So such data may be collected at regular time intervals. Now this is important. Regular time interval. That means the interval between the time periods, we have given t1, t2, and so on. The interval, that means t2 minus t1, which is the interval, should be exactly same. t2 minus t1 should be exactly same as t3 minus t2. The interval should be exactly same. That means either it should be monthly, weekly, or quarterly, or annually, right? The interval should be same. It should be 1 year, 1 month, 3 months, 1 week, daily basis 24 hours, but it has to be same. You cannot have a difference of 1 day and then difference of 3 days. That's not time series data. Time series data can be used and it is actually used a lot in statistic, econometrics, mathematical finance for different types of applications. For example, weather forecasting, whether there will be earthquake by geologists, and financial forecasting like loss, financial loss, and so on. So these are some of the things which are also useful. Time series analysis is very useful in these areas. So univariate time series is something that I've already told you. So univariate time series are type of series where you only have a single observations which is recorded over a regular time intervals, right? Like we said, stock price, right? Stock price. So stock price in period 1, stock price in period 2, period 3, and up to period n, where there are n periods. And you do not have any other variable, only stock price or only stock returns, one of these variable. Okay, you don't have any other variable. All right, when you're talking about time series, let's do a brief recap of what is a cross section data. So cross section data is a data where you use, right? Remember, we're talking about a number of variables at one time point. In time series, we had one variable at number of time points. It's exactly the reverse. One time point and different variables, right? So, say for example, you're talking about an individual firm, right? You're talking about what happens what happens to this firm in 2011, right? So that's the area of study. So you collected the number of employee, the revenue, the total profit of the company. So these are these are like the variables, right? And you collect all these things for one time period, that is 2011, right? This is called the cross section data. Multiple variables, one time period. Whereas in time series, you have one variable and multiple time period. If you take only profit in 2011, profit in 2012, profit in 2013, then you call this as time series data. So this is how time series data is different from cross section data. So we use the multivariate statistics or regression in cross sectional data, whereas in time series data you will use the univariate time series modeling. All right. So what are the pattern that you can find in time series data? So depending on the frequency of the data, so which could be hourly, daily, weekly, monthly, quarterly, you can actually find different type of a pattern in the data, and you can actually use that pattern to do the forecasting. So sometime your time series data could look like this, sometime it could look like this, okay, sometime it could be straight line, sometime very random, something like that, completely random. So this is totally constant, we cannot do anything about it. This is very cyclical, that means there's a clear pattern, but it's very predictable. You actually don't need a sophisticated time series model for all these things. This is very predictable series. This is like a sine x series, right? Trigonometric function. Whereas this is somewhat difficult to predict, so probably this is one series where you need time series model. And this one, which is completely random, when the series is completely random, you cannot actually predict anything. I mean, you cannot predict anything, right? And when it is totally straight line, it's the values are not changing, there's no point using a model. You can actually simply do a guess, and it will be perfectly okay. You do not need a model for all these things when it's a straight line. So you probably have a downward sloping time series data. We are using the GDP data for one of the state in India. Okay, so this is a downward sloping from 1961 to 2001. So you can say downward sloping data for GDP, and there will be an upward sloping data. So this is the typical example of an upward sloping data where the slope is upward, right? Upward trending, right? It's increasing over time, right? Sometime you will have upward trending and then downward sloping. So could be mix of both upward sloping and downward sloping. That could also be there, right? So this is a typical case where initially there was a downward slope and then there is an upward slope, right? So this could also be one of the So these are different scenarios or different types of time series that you probably will come across in real-time scenarios. So there are different components, and it can be broadly classified into trend, seasonal, cyclical, and the random components. If you these words are simply the English meaning or the meaning of the English word. I mean, the technical meaning is also pretty much similar to the meaning in English, right? So when we say trend, what comes to our mind is that either it's upward trend or it's downward trend. So if you use the definition, it's just a long-term pattern, right? It's just a long-term pattern in the data. Either it's upward, downward, or a mix of both upward, downward. So that's we call it as trend. And then we call it seasonal. Seasonal pattern is nothing but something that appears in regular interval, wherein the frequency of the occurrences is within a year or even shorter. For example, quarterly GDPs or maybe sales. So seasonal could be if you use sales data. So every December, right? Every December there is a peak because December is the holiday season, right? So you will see that sales data for most consumer companies or e-commerce companies in the month of festivals is actually at a very high level, or there is a peak at this month. So we call that seasonal data. That means it happens only in a particular season, and it should repeat within a year or less. Within a year or less, right? If it is happening over more than 2 years, 1 year, it's not. I mean, by definition, it's not seasonal, right? We'll see what that case mean. So next one is cyclical, right? This is also a repeated pattern, but this could go beyond 1 year, right? So this is one where the pattern could be more than 1 year. So typical examples could be the budget, right? Well, budget need not be just 1 year budget, right? It depends on the country, and when exactly is the budget happening, right? The budget doesn't happen on a particular month of a year in every country. It could actually change. There could be a random budget as well based on uh, if the government really changes within a year. So you see some sort of repeated pattern that is happening, right? Some sort of wave like pattern, right? And two important points: the cycles are not regular. That means you don't see it at a very regular interval of time. That could be up here and then long time and then up here and then suddenly another up a long time, and there is no regularity as such. And it also deals with it's also related to cases where it happens with a number of other cases, like economic recession, inflation, you know some monetary policy changes in the country and so on. So some factor really affects this. So it's not just because of some you know the time factor, like festivals or something. Festivals are uh, already pre-decided, right? But budgets are not. Budget could happen, or budget decision of coming up a new budget is actually random, right? Government decides when it's going to come up with a budget. So that's cyclical. And the last pattern is the random, and this is the easiest to understand. So random is like anything that cannot have a particular pattern, right? It's totally random, as it as the word says. You do not have any pattern. You cannot extract any pattern out of it. So it's totally random. So the idea behind univariate time series is that to use the past values of the series data to forecast future, right? So what are the variables of interest? It could be stock price, it could be GDP, it could be sales, and so on. You can use it for variety of purposes. Okay. So when we call a series as white noise, okay. So when we say series, it's just a series of numbers, okay. So series is nothing but a series of numbers. A stock price of Tata Motors, okay. Stock price of Tata Motors, say it is 100 rupees in day 1, 120 rupees in day 2, 125 day 3, 119 day 4. So this is known as a series. Okay, so where it's a series of numbers with a fixed interval, right? So when we call a series as white noise, so this is the definition. A series is called white noise if it is purely random in nature. So let epsilon t denote such a time series where it has zero mean and has a constant variance. So zero mean, that means it is like this. It is 50% up positive, 50% negative. So when you sum it, it actually zero. So if you take the expectation of the this term epsilon t, it's actually zero. So in white noise, the mean is zero and the variance is constant. Mean is zero and variance is constant. Hence, if a data shows a time series shows time series data shows white noise features, so it's considered as a white noise, then you should stop doing time series analysis. Okay, you should stop. There is no point. There is no point doing time series forecasting, because this is one series which cannot be used for forecasting. It's such a random thing. Random series cannot be used for forecasting, right? That's why white noise series cannot be used for forecasting. So if series is not white noise, then you can go for time series modeling. And then what are the models available? So we'll start with autoregressive models. Autoregressive models are the models where the forecasting is done based on the past values. So if yt is one is the current value, yt minus 1, yt minus 2, yt minus 3, these are past values. So yt is a function of the different past values, yt minus 1, 2, 2, yt minus 3 and so on, and the error term. But now question is how many past value to use, right? That's the main important thing. How many past value? That means will you take only yt minus 1? Will you also take yt minus 2? Well, we'll see how we determine that, right? The common representation or the model which is represented normally, and we call it the autoregressive model. Autoregressive or the AR model is always with a parameter, right? So when we say ARP model, that means there are P parameters, right? P number of parameters. If you have only this one, all these things are 0, then this is a AR0 model. Okay, AR0 model is yt is equal to beta naught, no y, right? If you have only yt minus 1, then this is a AR1 model. AR1 model. If it is AR2, then up to this much, right? Yt minus 1, yt minus 2. If it is AR3, then include this one also. If it's AR4, go next, and so on. Most of the times you will stop at AR3 and 4. You won't go beyond that, right? Because it will be like, I mean, intuitively you see today's stock price is related to yesterday's stock price and day before yesterday. But before that, it's a long time. That's a long gap. So we don't take after few series. And we'll see how to determine this actual p value. What is the best p value for forecasting, right? So how many number of past values you need to take, that we'll see. Next type of models are known as the moving average model. The moving average models are the one where you forecast by taking the error terms. So if you do a regression of yt with yt minus 1, right, with say beta 1 plus beta naught, you'll get error 1, right? You'll get an error 1. Similarly, if you do yt minus 1 with yt minus 2 plus beta naught dash, you will get error term 2. So in every regression, if you regress the series with its immediate past series, then you will get a error term, right? Epsilon 1, epsilon 2 up to epsilon n, right? Now instead of using past value, you can actually use this error term for forecasting. Right? This was one of the proposal, that instead of using the past values like white in the AR case, in the moving average case, you use only the error terms for forecasting, right? The representation is same, So we have replaced the past values of y with the error terms. So we do not have yt minus 1 anymore. Instead, we are using the et and then et minus 1 and so on. And remember that these ETs are assumed to be white noise. That means if you take the mean of epsilon t, it should be 0, and if you take the variance of epsilon t, it should be a constant. So it is 1, or it is a constant value. It doesn't change over time. The next type of models are nothing but they are known as the ARMA models, right? So they have both AR as well as MA representation. That means you use the past values and also the error terms. Okay. So in the representation, you will see you have yt minus 1, yt minus 2, yt minus 3. So you have the past values pretty much like your AR terms. So ARMA, this is called ARMA, right? Autoregressive moving average. That means you have AR term as well as MA terms. So you have past values yt, yt minus 1, yt minus 2, and so on. And then the error terms also. Epsilon t minus 1, epsilon t minus 2. So it's a combination of both AR plus MA is equal to ARMA. And people have said that this is more accurate many times uh, over AR or MA process. Alright. Now we introduce you to a very important terminology known as stationarity of time series model. So time series is said to be stationary if the marginal distribution of y at any time period is same at other points. Let me put it this way. The series has constant mean variance. So the basic statistic like mean, variance, all these things are time invariant. Time invariant. That means they do not change over time. So if you take a series, right, and you take such a mean in this period, and then you take a mean in that next period, you take in another period with the same interval, the mean should be same. And also the variance should be same. Although in reality many times it's not the case. Mean will differ and variance will also differ. So stationarity is one of the important criteria in time series modeling. So all the model that we have seen, AR model, MA model, ARMA, the requisite condition is that the series should be stationary. Otherwise we cannot use this model. So there, as I've already said, a series which is non-stationary can be made stationary after differentiating. And I will not get into the details of it. What when we mean by differentiating is nothing but taking the suppose this is something like that. Okay, you take the first derivative or take the second derivative and then you make it stationary. That is the procedure of doing that. And that's why in ARIMA model you might have heard about ARIMA. ARIMA, right? The I term stands for integrated, right? So ARIMA is the third. We talked about AR, MA, ARMA. So ARIMA is another type of model where I terms is there. I terms means integrated. That means differentiating. If we're differentiating once, we're calling it as integrated one series. If you're differentiating twice, then integrated two series and so on. So I0, I1, I2. If you are not doing any differentiating, it's already at stationary, then it's I0 process. If it is differentiating once, then it's I1, else it's I2 and so on. So from this slide, the takeaway point is that if a series is non-stationary, you have to first make it stationary before doing the forecasting. And how you make it stationary? By differentiating. So when a series is differentiated, what we call it? We call it as integrated. And what is the order? If you differentiate once, then it's a I1 process. If you differentiate twice, then it's I2 process. Okay? The series has to be stationary, right? Stationarity is very important from theoretical point of view. Okay, theoretical point of view. So if you try to do the estimation of time series models, estimation of time series model like ARMA, ARMA or ARIMA model, stationarity is one of the basic assumption. If stationarity assumption is not met, then estimation is erroneous or the forecasting is not reliable. So that's for theoretical point of view, checking stationarity in a series is very important. The estimation and forecasting of univariate time series is carried out using a very famous methodology known as Box-Jenkins methodology. So these are two statisticians or econometricians who formulated this strategy of doing forecasting. So Box-Jenkins methodology of doing forecasting is an important step or important methodology of doing time series forecasting. It involves three steps: identification, estimation, and then diagnostic checking. And remember, the Box-Jenkins methodology is applicable only to stationary time series. So the first thing that you need to see in a time series whether the series is stationary. So the moment you have the modeling in place, I mean you want to do the modeling, first you see if it white noise. If it white noise, don't do anything. Okay, you cannot do any forecasting. Don't do anything. Then check if it is stationary, right? If it is stationary, then start with modeling. If it is non-stationary, first do differentiating and make it stationary. Make stationary, right? And then you apply your time series model like ARMA, ARIMA, whatever. Right? That's the way. All right. So next terminology is what is known as a autocorrelation function. So autocorrelation, as the name suggests, it correlation with itself. That's why we would call as autocorrelation. That means correlation with itself. If yt is correlated with yt minus 1 because both are series and you can actually take a correlation, then it's autocorrelation because the same series is being taken used for calculating the correlation with the same past values of the same series, right? So it's autocorrelation. That means correlation with the same series. And why do we need to measure this? This will help us determining the p values or the parameters, number of lags. You remember I was talking about the number of lags to be used in the time series model. So we'll compute autocorrelation ACF function while doing the time series modeling. So we'll compute the autocorrelation value with this formula, which is covariance of yt, and then suppose we want to find out the correlation between yt and then yt minus p, right? Let's say t is equal to 5 and p is equal to 1. So what is yt then? Y5. What is yt t minus p? It is y4, right? So we'll now try to find out the correlation between y5 and y4, right? So that's just a representation. So how do we find it? Covariance of yt minus p. Just put the value of t and p. We have taken t is equal to 5, p is equal to 1, and you can have any values there. And it's just a correlation formula. Square root of var of yt is a square root of var of yt minus p. So you have this value, and then you find out the autocorrelation values. Okay, or the correlation. Autocorrelation is nothing but some sort of correlation, just that we call it autocorrelation because it is the correlation is taken with the same series. Normally correlation is always taken with two different variables, right? But it's only one variable, that's why we are calling autocorrelation. Another important thing is the partial autocorrelation. This is also some sort of a correlation, but it's slightly a variation of that. So partial autocorrelation, or known as the PACF, are used to measure the degree of association between yt and yt minus p, right? So all the time you remove the different lags between them, right? Say this is y5 and this is y1. So I remove y4, y3, y2, and then do these partial autocorrelations, right? So in that case, we call it as a PACF. So PACF is some kind of ACF, just that we remove the intermediate series between this intermediate lags. So there is no effect of y4, y3 and y3 in this case. We only see the effect of y1 on y5 without taking into consideration y4, y3 and y2. So why do we need to calculate ACF and PACF? Well, we need to calculate ACF and PACF just to see to what extent the current values of a series are related to past values. So the idea why we do all this thing, I mean, from common sense point of view, if you are forecasting a series, right, you are taking that okay, today's values are related to past values, but how many past values? Will the next past value, next of next past value, and next of that? How do you know how many past values related to? I mean, logically, if you think today's value is always related to yesterday's values, maybe day before yesterday's, therefore, maybe a couple of days. But after that, that should, I mean, ideally there should not be any relation, right? Like stock price. Stock price of today is related to stock price of yesterday, day before yesterday, maybe 2 days, 3 days. But beyond that, there will be very less correlation. That so ACF and PACF will tell us that to how many lags or how many periods you should consider for forecasting. So there you will be able to find out the lags. Lags means whether it should take t minus 1, t minus 2, t minus 3 or so on. So how many lags you should take. These are lags. Okay. So so what we do is to know that we plot what is known as a correlogram. Correlogram is nothing but the plots of the ACF function with respect to the lags. So by looking at the ACF and PACF with respect to the lags, we select the P and Q value in ARMA, P value in AR, Q value in MA, right? In ARMA we have two parameters, both MA and AR parameters, P and Q. So the general characteristics, or theoretically, what you can see is that if you are doing a ARP model, the ACF will be, there will be a spike and then it decays. The PFCF will spike and then cutoff will be towards 0. In the MA case, the spike cutoff to 0, and then PACF spike, it decays slowly to 0. In ARMA PQ, we will have spikes decays to 0 and spikes decays to 0 also. So these are some of the pattern, okay, normal pattern, a standard pattern of different time series models of pattern of ACF and PACF, and that's how you will get to know that whether you will use AR model, MA model or ARMA model, right? So you might wonder, right, why we have three types of time series model. Well, we have three type of time series model for three types of different scenarios or different pattern. So how do we know which one is best? By looking at the ACF and PACF, right? So if I'm doing a detailed analysis, nowadays it's not required, because nowadays softwares actually give us automatically, but if you do it on your own, you'll be more sure about it. So you can actually plot the correlogram, ACF with respect to lags and PACF with respect to lag, and see which one of them is true. If this is true, then use ARP. If this is true, then use MA. If these 2 points are true, then use ARMA. As I've already said, the first step in the modeling process to check the stationarity, and then do the estimation, and third, do the diagnostic checks, right? So 3 steps are very clear, I'm sure, because this is standard steps in most econometric models, where you start with diagnosis, whether which model is to be used, if the data series is perfect for time series or not, and so on, right? Then you do the estimation, and third, once you've done the estimation, do the diagnostic checks, just to be sure that your model is actually good enough for practical use. So there are different type of estimations are available. You can use the Ewell-Walker procedure for estimation, and then there are methods of moment, and then there is maximum likelihood method. So we'll not get into details of what these estimation methods are, but no matter what estimation you use, you never have to use because software themselves use it. You can specify though that which method is to be used, but there will be slight variation of that. You won't have a lot of variations, so no need to be worried about that. These are internal calculations what the software does for estimation, right? Maximum likelihood is the one which we all are familiar with. So because this is also one estimation method used in time series model, so we can use the same thing. Now once it's we have already built it, we'll do the diagnostic checking. So so what we'll do, we'll take look at a lot of this diagnostics or the statistics from the model, and we'll be sure about it only after be very sure only after we see that these values are at a comfortable range or acceptable range. Pretty much like you see R square, AIC, BIC in regression, right? You don't have R square here, but you have AIC, BIC, SBIC. So the model with the lowest value of above criteria is the best model. So what many a time the software does is that it randomly picks a number of models and will tell you which model suits your model best based on the AIC or BIC criteria. So let me tell you and give an example. So you will be worried whether I want to AR not model, AR1 model. So you are sure that you are using AR model based on the criteria we discussed in the last slide, right? Now you will be confused whether I should use this one, or AR2 model, or AR3 model, and so on. So what you can do, if you're not very sure, if you lack sound theoretical knowledge, you can simply fit all these models, okay, all these models, and take the one which is having the least AIC value or the least BIC value. That's the best fit for your model, right? So that's the way you need to do. And finally, for diagnostic purpose, you should ensure that you plot the residual SEF, the SEF of the residual, right? And it should be random, right? It should be random. That means the mean should be 0, and there should not be any pattern in your error, right? It's pretty similar to what you see also in regression, right? There should not be pattern in your error term, right? So diagnostic check is same what you should do in regression. It means you should ensure that the residuals are white noise. That means mean is 0, and that means there is no pattern in your residuals, right? So you can do that post the model estimation, and then you can use, once you are sure your diagnostic checks are fine, you can use your model for forecasting future. So these are the steps. We'll see an example, and probably will be better off. So here is a case study, and we'll do in R. So I have not given the plots here. You can use this course, and data set is given. You can try it out on your own, and see, and you can play around with different types of model and see the pattern and so on, right? So there are two case studies. So let's look at the first one. So in this case, I'll be using the ARIMA. So I'll use the AR, then I, and then MA. So when we combine, we call it ARIMA. AR means autoregressive, I means you are differentiating. It's a non-stationary series and we are differentiating. That's why it's I, integrated. And then we have moving average because this is MA. So autoregressive integrated moving average. Autoregressive integrated moving average. That means we are using past terms. We are also differentiating. We are also taking the error terms. So we are taking all three conditions and we calling it as ARIMA model. So we'll see how you build an ARIMA model. So this is a data set with death age of 200 individuals. So this is sort of a time series model. And then how do you do it? Okay. First, take it inside, do the plots, okay, and see if there is a pattern and all. Do some basic checks, okay, and then plot your SEF and PACF and see whether you should use AR, AMA, ARMA, or ARIMA, and so on. Or maybe you can build all models and see which one is the best or which one is giving your best results and so on. Not a big deal. If you have time, you can do that. right? So you need to install package forecast in R and use the function auto.arima and use your series, and it will provide you the best fit. So when you do that, our data set says that the ARIMA 000 ARIMA 000 is the best fit, right? So it internally computes everything. We do not need to do anything. Internally computes, do the comparison. It has done the comparison and it gives us that this is the best fit. That means the P lag is 0, the Q is 0, and also the I is 0, right? And it only has intercept. It do not have slope coefficient because there is no AR component, integrated component, or MA components. So slope coefficients are all zeros, right? And you also have the AIC and BIC. You can try out other models like ARIMA 001, ARIMA 100, ARIMA 111, ARIMA 101, and you try out all these things and look at the AIC values or BIC values, right? You will see that they're they're like more than this. So this is the best fit. It's automatically giving us. We can also try manually by looking at all these different forms. So you can check all these models on your own and come up with these values. You can check on your own using the same package, and then you will see that ARIMA 000 is giving you the best result. And then you can do the diagnostic plot. So what we do is simply plot your standardized residuals, and it should be white noise. What do you mean by white noise? That means it should be random. There should not be pattern in your error terms. Once you are sure about it, I mean the error doesn't have any pattern, then you can use this for forecasting. So how do you do forecast? Simply use forecast.arima and then just tell that for how many periods you want forecast. So you want forecast for next 10 periods, right? So this is the syntax. You use this and then you will get forecast for next 10 periods. So that's the way you do time series forecast, ARIMA forecast in particular. Some more codes you can use for your purpose, and we'll also see another case study in the next video.